In Disney's 1979 film The Black Hole, an explorer ship discovers the missing USS Cygnus parked at the edge of a massive, glowing space whirlpool. To explain how the ship avoids being sucked down this cosmic drain, the script relied on a magical anti-gravity field, a concept that bypasses the actual rules of how objects move in space. We are sending a hypothetical modern ship on that same flight path to test the film's 20th century physics against the data provided by modern astrophysics. Comparing the practical effects of 1979 with modern findings shows that reality involves objects being drawn out into subatomic streams while the outside universe passes by in a flash. Our ship doesn't actually require an anti-gravity field to park near the void. Because a black hole is simply a massive object, standard orbital mechanics allow us to orbit it just as a planet orbits a sun. However, the view from the bridge would not resemble a giant water drain. Instead, we would see the effects of gravitational lensing. This diagram shows how the black hole's mass acts as a lens, bending light rays from distant stars completely around the sphere. This light-bending property makes the classic whirlpool trope obsolete, forming a halo of trapped radiation. While stable orbits prevent us from falling in immediately, they leave the ship and crew exposed to relativistic hazards that the 1979 movie never addressed. On the cinematic Cygnus, the crew experiences the passage of time at the exact same rate as the rest of the galaxy. Albert Einstein's groundbreaking framework for general relativity explains exactly why this is impossible. Near a massive gravity well, the very passage of time begins to diverge. Because of time dilation, an observer on Earth would see our ship slow down and appear to freeze in place forever. Meanwhile, the crew looking out the window would see the rest of the universe age by thousands of years in an instant. As we drift closer, the acceleration becomes inescapable. We reach the point of no return, the event horizon. Here, the ship undergoes the physical destruction the movie glossed over. This is spaghettification, caused by extreme tidal forces. The gravity pulling on the nose of the ship is vastly stronger than the pull on the tail. The hull and everything inside it are stretched into a single-file stream of subatomic particles. While the ship is physically shredded, the central scientific question remains: what happens to the bits of information that once formed that matter as they cross into the dark? The film ended with the villain entering a fiery hell and the heroes escaping via wormhole. Science instead points toward a mystery involving quantum data. Stephen Hawking determined that black holes eventually evaporate. They slowly leak radiation until they disappear entirely. This creates the information paradox. If the black hole vanishes, the quantum data must be preserved, or physics itself breaks down. One leading theory to resolve this is the holographic principle. Rather than a magical afterlife, the ship's 3D information is flattened and encoded as two-dimensional data directly on the event horizon. The black hole acts as a high-density storage system, growing its surface by one tiny pixel for every bit of information swallowed. The 1979 vision relied on religious metaphors and simple whirlpools. The reality, where time stops, matter turns to dust, and three-dimensional life is encoded onto a flat surface, is the most complex landscape we have ever discovered.